Hey everyone, welcome back. We have made it to our last module, learning module of the semester, which is module 11 on cross-classified linear mixed models. So this has been really fun, and we've made it all the way. We've covered a lot of cool concepts along the way, and hopefully things have built in a way that makes some sense too. So I want to talk to you very briefly. I get this question a lot when students ask me about checking assumptions. Um, and this is a good question because when you read a lot of research reports, papers, articles, even presentations at conferences, you don't see too much talk about assumptions. And so that begs the question, how much should you talk about assumptions in a paper? And which assumptions should you check for and how often? So these are all really good questions because you hear, you have the exhausted list of assumptions in Garson and lots of good questions. So here's my recommendation. So a lot of this comes down to historically how academic publishing has functioned, and so academic journals have for decades been published in print. And so they have some very strict space requirements because each page in the journal is going to be physically printed, right, and costs quite a bit of money. And in addition to that, at least in our disciplines, in education research and related social sciences, there hasn't been a lot of good widespread methodological expertise among reviewers. And so it's hard to get reviewers, for example, for multi-level modeling, who really feel comfortable reviewing multi-level modeling papers. But both of these things are really changing. So my recommendation is, of course, to check assumptions and try as much as possible to incorporate what you've learned in class if you're doing multi-level modeling or other kinds of modeling. But you can always include a methodological appendix with your paper and or in your presentation. And that is something where you basically take all the hard work you've done testing assumptions and other things, and you put it in a separate location for people to look at if they're interested. So you can always briefly talk about the assumptions and kind of give a high-level summary, but then mention it in more detail. You can include plots and graphs, the stuff we learned about last week. You can include more detailed stata, I should say, and or R output. Robustness checks, code, all kinds of stuff. And a great place to put this, if you haven't checked this out before, is the Open Science Framework. And there's a link in this slide to visit this. So this is a free service that's provided by the Center for Open Science, which is affiliated with UVA. And the whole goal of this center is to make science more open, more reproducible, and more replicable. And so you can create a project on the OSF space. For example, here's a project I did looking at some machine learning. And you can include data, you can include scripts, you can include any related manuscripts, protocols. You can upload all this stuff to the website. And then the cool thing is you actually get a little link. So this website actually has a DOI, a digital object identifier. And you can cite this in your paper. So you can say, hey, if you have a question about this, go to this website for a methodological appendix, and you can look in more detail, which is really, really a cool and easy approach to this. All right, so let's talk about cross-classified linear mixed models, cross-classification. Okay, so last week was Module 10. We talked about how to check some basic assumptions of multi-level modeling using residuals and Cook's distances and fun things like that. So this week we're going to talk about cross-classified multi-level models, or cross-classified linear mixed models, which are the exact same thing. And this is a special case of multi-level modeling that is really flexible and useful in a lot of scenarios. So here's what it means if a person, a unit, a student, a participant is cross-classified. It means they're a part of two non-nested groups. So here's an example of that. So you might have college students who are nested in courses, but they're also nested in study groups. And maybe the courses and the study groups don't overlap. So maybe my friend is in another section of the same course and we don't share the same class, but we do study together. That would be an example of cross-classification. You also might have clients who are nested in specific therapists, right? So they work with a specific therapist, but they're also nested in different peer support groups. And those peer support groups might contain people who have lots of different therapists, and it's a larger group that is not sort of perfectly nested within that one person. You might have professors that are nested within departments, but they're also nested within academic degree programs. So, for example, at VCU, we have the Curriculum, Culture, and Change program, which is really a shared program between the Foundations of Education department and Teaching and Learning. And so really it's affiliated with both. And so professors could be affiliated with one of those departments, but also this program. So there are lots of other examples of this kind of structure. So this is what we call a not perfectly nested or perfectly hierarchical structure. But we can actually extend the multi-level modeling framework to handle this. So we do have some really nice solutions. So the key idea here is that many research scenarios are actually pretty messy. So we assume kind of a perfect hierarchical structure like this. So this is an org chart, right? If you've ever worked in an organization, you've probably seen one of these. So this sort of shows how all the different elements of an organization relate to each other. And usually they start down here at the bottom, right? And everything sort of filters up to one level at the top. So here the superintendent and board of education sort of filters down into these offices, and each of these offices has a director, and each one of those has all these functions. And that's what we assume a lot of times when we think about nesting. But actually, the reality is often quite a bit more complicated. And this is just, I think this is a freeway in LA. It might be I forget which one, but, a lot of times you don't have that clean kind of nesting. A lot of times these factors will overlap quite a bit, and you have to kind of pick them apart a little bit. For the sake of simplicity, it is important to think about keeping things simple, but some things that we're interested in are necessarily more complex. And the example we're going to talk about today is students who are nested in schools, which is one of the most common nesting scenarios that we looked at in multi-level modeling, at least in the social sciences. But students, right, their whole reality is not school. So they also are nested in where they live, their neighborhoods. And so that is much more of a situation like this, right, than like this. It can be much more complicated. So that might be a useful kind of picture. So let's get a look at what this cross-classification means in very specific terms. So this comes from chapter 11 of Garson. I really like Garson's drawings. I think they're simple but really powerful to convey the meanings. So what Garson's done is he has visualized this situation where students are nested within schools and also within neighborhoods. And so we can see here, level 1, that's typically the lowest level that we're talking about. We have students, and each one student here is indicated by an S. So student 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 2,000. And I should say this is, we're talking about a specific situation here. This is the data set called the Scotland data set, which we're going to be working with in our demonstration and also in your content review. So this is a study that was conducted in Scotland looking at kids' educational attainment. And the authors, George Leckie and another handful of folks, collected information not only about where kids went to school, but also where they lived. And so this is kind of a natural cross-classified situation. So here we have students that are nested, students at level 1. We have a bunch of students. And unlike a typically hierarchical structure, so if this was perfectly hierarchical, right, students would be nested in, say, classrooms here at level 2. And each one of these classrooms would be nested within a school at level 3, for example. And notice, students are not cross-nested, right? They only belong to one classroom, and that classroom only belongs to one school. That's a hierarchical structure. This is a cross-classified structure. In some ways, keep in mind, it's more realistic, but it's also messier. So now we have what Garson calls level 2C and level 2R. You could also call it level 2A and 2B. So essentially, each student belongs to a school, and that looks pretty clean. But then below, each student also is drawing from a specific neighborhood in the city. I think the city was Glasgow, but I'm not sure. Might have been Edinburgh. But so we have up to 500 neighborhoods in 17 schools. So notice the crossing that goes on here. So student 1 belongs to neighborhood 1 and school 1, but student 2 actually belongs to neighborhood 2 and goes to school 1. Student 6 belongs to school 3, but they also live in neighborhood 1. So you have some crossing in that structure, and that is called a cross-classified structure. So that's the type of situation that we're talking about with these types of models. Okay, so a few notes about these. Just like ignoring regular clustering or hierarchical nesting can bias your estimates in regular regression. So if you run a regression, but you should run a multi-level model, that can bias your estimates, particularly the how you're treating the error in the model. Cross-classified models have the same problem. So if you have a cross-classified situation, you should use a cross-classified model to address it. And Garson notes in his book, and I think that he's absolutely right about this, that probably most of the situations we think about actually end up being cross-classified, but for sake of simplicity, we just turn to a regular MLM, which imposes some problems. So Garson outlines a few kinds of cross-classified models. I'll tell you right now, we're going to focus primarily on the first one. This is what Garson calls an additive cross-classified model. And what that means is we estimate the error variance separately for school and neighborhood, or whatever your cluster variables are. And we don't estimate separate terms for the interaction between school and neighborhood. We do account for overlapping membership. So it does account for the fact that kids are sort of in overlapping clusters, but not with a specific interactive term. In order to do that, you need to run what's called a non-additive model, and that estimates a specific interaction term that's random for each one. This is actually quite complicated to estimate. I would refer you to Garson for this one. We're going to focus primarily on what are called additive cross-classified models, because those are the ones that most people think about and can be the most straightforward to estimate. So a little advice for running cross-classified models. Again, I'm pulling from Garson here, chapter 11. I think he has some good tips. One, I recommend starting simple. Start by running separate null models for each of your clustering scenarios. So start with running a null model just looking at school, and then run a null model just looking at neighborhoods. That helps you, because we know we can sort of wrap our heads around a regular null model pretty easily. And so it allows us to kind of ease into the more complicated structure by looking at the separate null models first. And then it also gives you an ICC for each one of those relationships too, which can be really helpful. Garson also recommends that you pay attention to which of your clustering variables has more levels or groups. And he recommends putting the variable with the fewer number of groups first, and in the random portion of your model. And that's the sort of section with the double pipe operator, and then the colon in stata, or in R, each random effect is in parentheses like this with a 1 with a random intercept. So he would recommend ordering wise to do school and then neighborhood. This tends to be a little bit easier with convergence. You have fewer convergence problems, and it's a little more efficient. It's not required, but it's helpful. And then another great piece of advice, use the same model building process that we've used all semester long. Add predictors gradually by level, so student level, school level, neighborhood level, all together. And you can test fit using AIC and BIC, and save those fancier components like interactions and random slopes for last. So really the application of a cross-classified model is very similar to a regular multi-level model. It's just being aware that it exists is one of the key elements. So just a note here, I have annotated output here for a regular, we call an additive cross-classified model in Stata, as well as in R. I've got the interpretation and where to look. So if you're looking to write these up, you can sort of see how the coefficients are interpreted. And I, of course, do the same thing on the videos. So I think you probably have enough to get started. That is cross-classification. Pretty fun. Good luck, and we'll talk to you soon.